Hello everyone. Our topic is LC3 concrete. L stands for limestone, C3 stands for calcined clay cement. Moving forward, introduction part is limestone calcined clay cement holds promise as a new type of sustainable cement-based material. Most of the improved properties of LC3 have been associated with its refined microstructure compared with Portland cement materials. LC3 is a novel low-carbon cement comprising up to 60% less clinker, achieved through the combined use of calcined clay and limestone as SCMs. SCMs stand for supplementary cementitious material. It boasts widespread availability of its components globally, ensuring low cost production and reduced embodied CO2 emissions. Moving forward, the purpose of LC3 concrete. Limestone calcined clay cement, which is LC3, is a new type of low carbon cement that can first low carbon cement with cost effective. Second one is offering a 30% reduction in CO2 emissions compared to Portland cement. Third one is LC3, a low carbon cement, replaces up to 60% of clinker with limestone and calcined clay. Fourth one is it is more environmental friendly. Fifth one is excellent mechanical properties and durability compared to ordinary Portland cement. Raw materials which are used, first is calcined clay, second one is industrial limestone, third one is gypsum, fourth one is cement clinker, fifth one is natural sand, and sixth one is Phillips metal, and last epoxy. Moving forward, chemical compositions of the kaolin telling from X-ray fluorescence, which is given in this table by percentage weight. SiO2 has the largest weight by percentage by weight, and L2O3 is the second largest one. And so on. Moving forward, preparation of cement paste samples. First step is preparation of OPC and LC3 paste samples. In this step, mixes were prepared following proportions listed in table 3, which is given below, excluding sand. Second step is moisture curing. In this step, samples were moisture cured for 24 hours at 20 degrees Celsius, then demolded. Third step is immersion in calcium hydroxide solution. In this step, demolded samples were immersed in saturated calcium hydroxide solution until reaching a specified age. Fourth step is sample processing. In this step, hardened samples at a specific ages were cut into a small pieces. Fifth step is hydration arrest. In this step, cut samples were immersed in isopropanol to halt hydration process. This is the table 3, which is mixed composition of OPC, CC30 and LC3 binders. Moving forward, preparation of cement mortar samples. First step is preparation of OPC and LC3 mortar samples. Second step is mixer design. Third step is moisture curing, followed by super plasticizer applications, and last one is slump measurement. This is done by the preparation of OPC and LC3 mortar sample. In this step, proportions adjusted to maintain a calcined clay to limestone weight ratio of 2:1 in LC3 specimens with 50% clinker to cement ratio, which is followed by mixture design. In this step, gypsum added to all mixture to prevent under sulfation conditions. Mortar samples molded in prees, which has size 40 mm into 40 mm into 60 mm, 160 mm, sorry, as per EN 197 1 standard. Next step is moisture curing. In this step, samples cured for 24 hours at 20 degrees Celsius, then demolded and immersed in saturated lime solution until a specified age. Next step is super plasticizer applications. In this step, 0.1% polycarboxylic waste super plasticizer used for LC3 motors to maintain comparable flow rate to OPC motors. Last step is slump measurement. In this step, average slump values of OPC and LC3 measured 219 mm and 120 mm respectively for EN 196 standard. Moving forward, test and results. So I'd like to invite Ayush Raj to go further. Thank
Thank
you.
you, Gaurav. And now my presentation topic is tests and results. Next slide. First, mechanical testing. Mechanical testing, the first point is testing procedures, compressive and flexure strength tests conducted according to EN 196 1 standard. Second point is sample preparation, 24 model specimen of LC3 and OPC prepared and examined. And third point is girls and clay reactivity test 6 cc 30 specimens tests tested for compressive strength at 28-day age to calculate a strength activity index per EN 196 1 standard. Fourth point is importance of ACI test. ACI test widely recognized for assessing the activity of supplementary cementitious materials ACMs like sand clay, providing reliable evaluation of their polyolenic activity in cementitious materials. Next slide. Results and discussion. First one is compressive strength comparison. LC3 model shows slower initial strength development and compared to OPC, but achieves comparable and sometimes higher strength value at later age. Second point is reactivity analysis strength activity indexes. Test indicates high reactivity of calcined clay in LC3 motor with CC30 motor displaying an average ACI of 93.2%. Third point is flexure strength performance. LC3 exhibits excellent flexure strength comparable to OPC from 3-day curing and surpassing OPC by over 20% at 180-day curing. Fourth point is correlation analysis. Power correlation between flexure strength and compressive strength established for LC3 and OPC showing higher flexure compressive strength ratio for LC3, especially in samples with higher compressive strength and more curing days. Fifth point is comparison with empirical equations. LC3 flexure compressive strength equations show a higher slope than OPC. Next slide. This is a graph of compressive strength and versus time and flexure strength versus time. Next slide. Microstructure and characterization. First one XRD analysis. Fields, meter intrusion, policing, ACM-BAC imaging. Next slide. XRD analysis. XRD analysis is conducted using CUKA radiation on a D8 advanced instrument at room temperature. A scan from 5 to 70 degree with a step size of 0.016113 degree 20. Cement paste samples were ground into a fine powder and tested after hydration stoppage. Next slides. Results of XRD analysis. XRD analysis of LC3 and OPC paste examined crystalline phase affecting microstructure and mechanical properties. LC3 displayed more phases including AFT port landed, HCMC and reactivated mineral compared to OPC. Phase identification C2S and C3S peaks in OPC remained strong until 28 days, indicating dilution. LC3 saw no clear kaolinite peak due to its non-crystalline nature, but muscovite and quasi reflection were observed. Third point is formation of carboaluminates. Intensity of carboaluminates and AFT crystals increased after 7 days in LC3, possibly contributing to enhanced mechanical properties due to bridging effect with the matrix. Fourth point is absence of AFM in LC3. Dissolved carbonates in LC3 solution inhibit AFM formation favoring SC and MC. Fifth point is port landites content lower in LC3 and OPC attributed to dilution effect at early age and polyolenic reaction with calcined clay at later age, leading to gel formation. Next slides. Next slides. These are the XRD pattern of hardened LC3 and OPC paste at the Next slides. Next slides. Polishing test. Polishing test is the first point is mounting in epoxy. Samples were mounted in epoxy with a fixed epoxy hardened ratio of 25:3. Second point is two-stage polishing. So first stage is sandpaper of 4 grades, 125 micrometer, 58.5 micrometer, 25.8 micrometer, and 115.3 micrometer was used for initial rough polishing. And second stage is fine polishing was conducted using polishing cloths with 4 grades. Ethanol diamond, grid polishing, suspension of 6 micrometer, 1 micrometer, 0.25 micrometer, and 0.1 micrometer. Third point is rinsing and sonication. After each grade size sample were rinsed with ethanol and sonicated in an ethanol bath to remove polishing debris. Next slide. Now forward to Soumya Siri. Hello.
Thanks,
Hello,
Ayush. So
Soumya.
now I'll be discussing. Now I'll be
Yes, go
discussing
on, go
about
on.
the field's metal intrusion test. Next slide, please. So these are the processes. First is melting Fields metals. Fields metal with a low melting point was melted at 80 plus minus 2 degrees Celsius. Intrusion process. The molten metal was intruded into hardened test samples using a steel die. Third is pressure application. Pressure was applied gradually using a CIMA DZU AGX testing machine reaching up to 400 MPa at a rate of 12.5 MPa per minute. Fourth is pore size target. The pressure was calibrated to include pores of approximately 3.6 nanometer in size. Fifth is imaging resolution. The theoretical minimum imaging resolution was determined to be 5.88 nanometer based on Monte Carlo simulations. Sixth is temperature control. The surface temperature of steel die was maintained at 80 plus minus 2 degrees Celsius to ensure the sample temperature remained above 70 degrees Celsius throughout the process. Pressure duration. The peak pressure was sustained for over 30 minutes to ensure proper intrusion. Cooling. After the intrusion process, the sample were cooled to room temperature for further analysis. Next slide, please. Next slide. So the next test is SEM BSc imaging analysis. First is instrumentation. The FEI NOVA NanoSem 450 FPG SEM was utilized for imagining the cement paste microstructure. Second is sample preparation. Polished cross sections of all specimens were coated with a 10 nanometer thin carbon layer before imaging. Imaging parameters. Backscattered electrons were employed for imaging. Using a voltage of 5 kilovolt, magnification of 1000x, and an electron beam dwell time of 10 microseconds. Fourth is image acquisition. More than 5 images were captured at random non-overlapping positions near the center of each sample, with over 50,000 pore profiles in each image. Fifth is data analysis, where it itself consists of 5 stages, which is first one is image processing. Images were converted to 8-bit grayscale and segmented into pore. Second is threshold determination. An iterative selection method was used to determine the optimal grayness threshold, providing cleaner extractions of the object region. And the third is binarization. PSC images were binarized according to the required threshold, where white pixels represented pores. Fourth is pore volume quantification. Pore volume was quantified by integrating the area of pores and the average volume fraction of pores was calculated. Fifth is local porosity analysis. Local porosity around unhydrated particles surrounded by hydration products was analyzed by a plot fill algorithm from binary images. Next slide, please. Next slide, please. So here are the results and discussions using metal intrusion and SEM BSc imaging analysis. Let's talk about the overall pore structure characteristics. So first is color map generation. A color map indicating equivalent pore diameter was generated based on high contrast between solid and pore phases in LC3 and OPC samples. Darker regions in the color map correspond to hydrates and unhydrated cement, enabling direct visualization of the global pore structure. Second is pore structure comparison. Both LC3 and OPC paste underwent densification as hydration proceeded, with LC3 displaying a more refined pore structure. LC3 showed reduced pore size compared to OPC at corresponding curing edges, indicating a compact microstructure. Next slide. So let's talk about the pore structure comparison in this graph. The ABC figure is showing the equivalent pore diameter of OPC at 7 days, 28 days, and 188 days. And DEF figure is showing the LC3 equivalent pore diameter at 7 days, 28 days, and 180 days. Here we can see that both LC3 OPC paste underwent LC3 demonstrate a higher fraction of finer pores compared to OPC at 28 days and 188 days, indicating the more refined microstructure. And we can also see that the fraction of large pores reduced significantly in LC3 from 28 days to 180 days during supporting its densification trend. Previous slide. Now let's talk about the microscopic insights. SEM-BSE images revealed pores in LC3 surrounded by solid phases, indicating the formation of more hydration products away from cement grains. Second is pores in LC3 were blocked by calcined clay particles, suggesting a filler effect of supplementary cementitious material. Next slide. Next. Now let's talk about the local pore structure analysis. So first is SEM EDX elemental mapping. Clinker, calcined clay, and limestone particles were identified using SEM EDX elemental mapping. Elemental maps of calcium, silicon, carbon, and aluminum were generated to distinguish different solid phases. Local pore structure analysis focused on the perimetric regions around these solid phases. Second is porosity distribution. Both LC3 and OPC samples showed highest porosity near solid phases particles, decreasing with increasing distance. LC3 exhibited constant perimetric porosity between 1 and 2 micrometer thickness, indicating limited particle packing efficiency. Third is early age porosity. At 7 days, localized porosity near limestone particle was higher than other solid phases, which affects the mechanical properties. Limited reaction of limestone led to porous perimetric structure, contributing to higher porosity and lower strength of LC3 compared to OPC. Next slide. Next slide. So this is the graph you can refer for the porosity of solid particles in LC3 and OPC. Next slide. Now let's talk about the aspect ratio of pores. First is experimental analysis. SEM-BSE imaging via Fields metal intrusion method enabled the analysis of average pore aspect ratio. Aspect ratio limit set at 4 as over 95% of pores lie below this limit. Second is comparison between LC3 and OPC. LC3 and OPC exhibited similar aspect ratio, which is mostly in between 1.8 to 2 at all ages. LC3 shows slightly lower aspect ratio for pores with nominal diameter greater than 10 micrometer, indicating lower pore connectivity compared to OPC. Third is implications for pore shape. Pore aspect ratios in cementitious material was found to be more than 1, challenging the assumption of cylindrical pores, whose aspect ratio is 1. Actual pore shape should be considered for accurate evaluation of pore structure, especially in porosity and pore size distribution calculation. Fourth is future research. Further studies needed to explore how pore and solid phases shapes influence mechanical properties of cementitious material. So these findings emphasizes the importance of considering pore shape for accurate assessment of pore structure in cementitious materials and highlight avenues for future research. Next slide. So this is the graph that is related to the aspect ratio of pores of LC3 and OPC paste at 7 days, 28 days, and 180 days. Next slide. So now let's move on to the conclusion part. So these are the sum of the points. LC3 showed superior flexural strength compared to OPC with over 30% higher strength from 7 to 180 days. Secondly, synergistic reaction between calcined clay and limestone led to the formation of significant carboaluminate hydration LC3. Third is LC3 exhibited a refined pore structure with lower overall porosity and reduced pore volume compared to OPC. Fourth is metal intrusion enhanced SEM imaging provide direct visualization of microstructural evolution in LC3. Fifth is thinner peripheral microstructure around solid particles in LC3 contributed to denser microstructure and enhanced mechanical performance. Sixth is LC3 demonstrates promising potential as a superior alternative to OPC in cementitious applications. So thank you. So these are the references that we have taken.
Thank you to all for presenting this LC3 concrete.